Today we're going to be talking about the number of lanes. You ever wondered how someone might determine if you needed one lane or maybe two lanes for vehicles to travel on, or maybe even three lanes for vehicles to travel? Well, one way you can do that is by manipulating this equation. And we'll go over what each one of these variables mean, but this one right here is the number of lanes. And so here are what each one of those variables mean. Maximum number of passenger cars for a desired level of service right here. And just so you know what level of service means, it is a way of representing the flow of vehicles. And it's a way we just kind of grade the traffic flow and operations. So here you have level service A, B, C, and D. And just so that you know, there is such thing as having a level of service E or F. Now, we wouldn't desire for a roadway to have a level of service A all the time, including the rush hour traffic, because that would just mean we would have to design for, I don't know, there's 3 lanes showing here, so maybe, I don't know, 20 lanes. That means no matter what time of the day, it's always going to look like this, not many vehicles on the road. Well, we're okay with having this many vehicles on the road, or a situation where you have this type of arrangement of vehicles, even if it was just for 1 hour of the day. Level of service E is sometimes desired, or acceptable, I should say, if we're only experiencing this type of traffic during the peak hour or the rush hour. We don't want a level of service F, which is a bunch of backup and congestion. But we're okay with that happening just for an hour a day. For the rest of the time, if it looks like A, B, or C, it's okay. So that's why we have here that this is the passenger cars for a desired level of service. So that really determines the number of vehicles, to be honest with you. This is the highest number of vehicles in a peak hour, so that's your peak hour volume. So that V is going to be in vehicles per hour. You're going to have the peak hour factor, unit list here. Another factor that's unit list, heavy vehicle factor, familiarity factor. We typically give that a sign of a 1. In an unfamiliar place, we might decrease it to a 0.85, but in most cases it's a familiar road, people are familiar with it, we'll give it a 1. And then of course you have your number of lanes, so this can be modified. Okay, this is what it looks like when it's modified. You can see here all I did was just switch these 2 spots here. Sometimes you might see this being called maximum service flow rate, so they kind of mean the same thing, just in case you see it in a different way. And that's about it. Again, this big V right here is vehicles per hour, and this is passenger cars per hour. So we just changed that into being represented in passenger cars. Ideally, we want everything to be represented in passenger cars so that we can have one unit that we are designing for. Key things worth pointing out here is that if I were to isolate just a few variables in this equation, you would notice that this equation right here factors in a lot of things. For instance, if I were just to isolate these 2 here, I would see that this is really equal to my design hourly volume. So my design volume is equal to the peak volume divided by my peak hour factor. Or if I wanted to isolate these 2 variables, I know my PCE, which is my passenger car equivalency, is equal to whatever the volume of vehicles, is, divided by the heavy vehicle factor. And I will be able to turn my VPH, vehicles per hour, into passenger cars per hour just by taking the vehicles per hour and dividing by the heavy vehicle factor. So that's one way you can represent all of your vehicles in passenger cars by itself. And so that's incorporated into this equation, and design hourly volume is incorporated in the equation as well. And there it is. You have your design hourly volume is peak volume divided by peak hour factor. Passenger car equivalency is the volume of vehicles per hour divided by heavy vehicle factor. Okay, now we're going to get into a quick example. The information is shown to you right now, but before we go any further, I'm going to let you know that for this example, we're going to be referencing this table, and we're going to reference this graph. This table and this graph are linked to one another. So the information that's shown here, you'll also be able to see it here. Except this is a little bit more detailed. It gives you a little bit more information than just the 60 mile per hour, 55 mile per hour, and 50 mile per hour free flow speeds. One more time, we're going to be referencing these two. So in this example, you have you're given 630 vehicles per hour were traveling or need to travel, and then you have a peak hour factor of 0.48. If you don't know what that is, go back and look at the video of peak hour factor. You have a heavy vehicle factor of 0.88, gives you indication of how many trucks are affecting the passenger cars that are on the road, and also your familiarity factor of 1. And so what we're asking for is how many lanes are required to sustain a level of service A. And if you remember, a level of service A looked like this. And so we want this level of service A, or we want the roadway to look like this, even when we have 630 vehicles per hour arriving on that road. You have the equation that we already talked about, and now we're going to go through with the solution. Now, most of the information here is already given to you, so this should be a pretty much straightforward example problem. Okay, one small note, one small addition that needs to be given to you was the speed, all right, the desired speed or the speed limit on this roadway, which is 60 miles per hour. Okay, so now we've kind of filled in all the information that was given. You got the 630 here, 0.48, 0.88. Each one of these things can really be determined individually, but for the sake of this example, we just gave it to you to make it really, really simple. Also, we know that F sub P is going to be 1. What we don't know is this maximum service flow rate, all right? So what we have to do is go to the table, and that's where this 60 miles per hour comes into play. Now, this table shows you the different items here per level of service, desired level of service. So if you only wanted, I don't know, 18 passenger cars per mile per lane, then you know you would have been in a region that would provide your level of service B. In our case, we want a level of service A, and we know that we need to figure out what our maximum service flow rate is, MSF. Also, previously I wrote it as V sub P. So if we figure out what this is, then we can solve our problem. So you can see here that level of service A and maximum service flow rate to maintain the level of service A is going to be 660. So I can go ahead and put that 660 right here. 660. And eventually I could just solve it out. But I didn't want to just show it to you there. I also want to show it to you on this sheet here. This sheet is showing you the speed flow diagram, speed and flow rate diagram, and the flow rate down here is in passenger cars per hour. That way, because it's passenger cars, you know that you're probably dealing with either that or that, which are the same thing, maximum service flow rate. And so we can pretty much find that same number using this speed flow diagram, which is designed for multi-lane highway. There are different ones. As a matter of fact, look at this one here. It's for a freeway. But for the purposes of just being consistent in the class, we're going to really just be using multi-lane highways. So at 60 miles per hour, you notice that vehicles pretty much maintain their speed until they get to a point where there are a lot of vehicles on the road, so there's 26 passenger cars per mile, and the level of service is at its boundary. So it's no longer a level of service C, it's about to change from C to D. So this is a C boundary, and then it starts to decrease. Now if I were to continue with the speed flow diagram, here's what it would look like. Alright, where that would be your max capacity, max volume, also known as capacity of the roadway. And you can see here, once you reach your capacity, your speeds start to drop, and if you continue to add vehicles, your speeds start to drop to the point where we're at a standstill. But for the purposes of answering the question, what we wanted to know was, at level of service A, traveling at 60 miles per hour, the maximum flow rate is going to be about, look at that, that's 600. This looks like it's pretty close to 660, which is what I found here as well. So, looks like I could use either the table or the figure to get my 660. And here's the answer. Number of lanes, 2.5 lanes. But what if I changed it? What if I said I wanted to figure out what the number of lanes required to maintain a level of service C at all times? So now, no matter if it's congested or not, I want it to always look like this on the roadway. Whether it's peak hour volume or rush hour or not, it's going to still look like this or better, level of service C. Well, I would assume that I would need less lanes because less lanes would provide more traffic. But let's see if that is the case. I would need to go here. And going down to the level of service C now, the maximum service flow rate that I use in my equation is going to now be 1550. At 60 miles per hour, same thing. Level of service C, that is the boundary of level of service C. That means it's transitioning from level of service C to D. If I were to draw a straight line, it would be right around 1550. So if I place that 1550 right here, I end up getting an answer that is equal to 0.95 lanes. Now you may be asking yourself, how can you have 2.5 lanes, or how can you even have 0.95 lanes? Good question, but here's the answer. It is possible for you to know that you definitely need 2 lanes, but maybe there's something else. Maybe you need a shoulder lane, or maybe you can have a situation like this where you have 2 lanes going one direction, but I don't know, maybe you have one of these two-way left turning center lanes in the middle. So it's 2.5 on this side and 2.5 on the other side. Maybe it's a truck climbing lane. It could be many things. Even be a situation where you have 2 lanes going in one direction and another 2 lanes going in another direction, but during certain times of the day you need to reverse this middle lane. Say during morning rush hour you need to have 3 lanes, and during afternoon rush hour you need to have 3 lanes going in the opposite direction, and so you have this middle lane, which is called the reversible lane. And sometimes you see things like this in big cities. DC is very popular for having these types of things.